All right, today we are going to talk about random forest. Last time we already discussed the trees, and we've seen that trees can easily overfit to data sets. Random forest is a way to get rid of these risks. It's the ensemble method. So we are going to see the details of how to put together maybe hundreds of trees and get rid of the overfitting problem as well. Ensembles are methods that combine multiple machine learning models to create more powerful models. There are many models in the machine learning literature that belong to this category. However, there are two ensemble models that have proven to be effective in a wide range of datasets for classification and regression, both of which use decision trees as their building blocks. These are random forest and gradient boosted decision trees. If you check the computations on the Kaggle, you would see most of the times these are the winner algorithms, not the so funny deep learning algorithms, interestingly, but these two ensemble models are the first models you need to try in your projects, okay? However, I will not cover the gradient boosted decision trees in this lecture. You can learn by yourself. Therefore, today we are going to talk about and see the details of random forest. As we observed at previous class, a main drawback of decision trees is that they tend to overfit the training data. Random forests are one way to address this problem. A random forest is essentially a collection of decision trees, where each tree is slightly different from each other. The idea behind random forest is that each tree might do a relatively good job of predicting but will likely overfit on part of the data. The keyword is that on part of the data. As I explain in a moment, we are not going to use the whole data set for each decision tree, but we are going to use some part of the data set to train each decision tree in that collection. If we build many trees, all of which work well and overfit in different ways, still the trees can overfit. We can reduce the amount of overfitting by averaging their results. This reduction in overfitting, while retaining the predictive power of the trees, can be shown using rigorous mathematics, but due to our scope, we will not go into very details of these mathematics, but I will try to give you an insight how they work, how they interact with each other. To implement the random forest strategy, we need to build many decision trees. So random forest ensemble strategy. So we need to put many decision trees together. Each tree should do an acceptable job, I mean the accuracy, of predicting the target and should also be different from the other trees. Why it should be different? Because if they are similar to each other, then they can overfit to the data, partial data, similar to each other. So we cannot have any different result as if we are using single decision tree. But here is the idea that we have to end up with in that forest with different decision trees, deciding differently from each other. So we need to train them differently. Random forests get their name from injecting randomness into tree building to ensure that each tree is different. Therefore, we are going to use two methods to differentiate these trees in training process. These two ways are either we are going to select the data points used to build the tree. So when we say that build the tree, we mean that train the tree. And by selecting the features in each split test. So in each split test, it means that remember the test. So test in that case is the question. Remember, in the decision tree, each node has a question. For example, does it has a tail or not, feather or not, can it swim or not? Remember the animal decision tree? So at each node in the tree, we have a question. This question is called test. So here what's saying that we can select the features to be used in these tests. In other words, in the data set, maybe we have 10 features. In decision tree, we can use any of these features in the test, in the questions. But here in the random forest, we will decide the number of features can be used in each decision tree. So if in the test set, in the train set, we have 10 features, we can limit these to 3 when creating the random forest, the decision trees. So it means that randomly, we will select only 3 features to create our decision tree. Therefore, we will select randomly these features, not any 2 trees in the forest be similar, because they are selecting different features. Okay. Let me show you more details. To build a random forest model, you need to decide the number of trees first. So how many trees will be in that forest? Let's say we want to build 10 trees. So here, basically, you see that in the orange, we decide the number of trees. These trees will be built completely independent from each other. So the algorithm, the ensemble algorithm, random forest, will train each of these trees separately. And while training these or building these trees, the algorithm will make different random choices for each tree to make sure trees are distinct. So they have distinct questions in test points and distinct decisions, boundaries. To build a tree, we first take what is called a bootstrap sample of our data. So far, I introduced how we select the features or limit the number of the features in the data set to create or to build the tree. I randomly select these features at each node, at each test, at each question. Now, we are gonna limit the number of the samples. So we are now splitting the data set for each tree. So each tree will see different part of the data set. I will explain now this process. It is called bootstrap sample. That is, from sample data points in the train set, we repeated the drawn an example randomly with replacement. Here is the keyword replacement. Replacement means that when you select a sample from the data set randomly, in the next selection, you can still select the same sample. So you don't remove the selected sample from the train set. So you are gonna keep selecting from the same data set randomly n number of samples. Thus, in the end, we can create a data set that is as big as the original data set, the training set, but some data points will be missing from the training set. However, some samples in the selected set will be repeated, duplicated, maybe tripled, maybe 4 times. Okay, let me give you an example of how to bootstrap. Let's say that we have to create a bootstrap sample of this list. In that list, we have 4 samples, A, B, C, D samples in that trained set. Now we will create the same number of samples in new sets You see that in two sets here. Let me show you. This is our original train set. Okay, this is the train set. Okay, let's assume that we decided to create two trees, decision trees. And for these two decision trees, we need to create two data sets, train data sets. Okay. Two. How can we create? We want to create these two data sets should be different from each other so that these two trees will be different from each other. So how many trees in the forest? We need this number of data sets created from that original. And when we use the bootstrapping, this will be the data set 1, and this is gonna be the data set 2. The number of the data samples in the data set 1 and data set 2 will be equal to the number of the samples in the train set. You see that we have 1, 2, 3, 4 samples in train set, and in DS1, 1, 2, 3, 4, and DS2, 1, 2, 3, 4. So by using DS1, we are gonna train the first tree. By using the DS2, we are gonna train the second tree in the forest. How can we create DS1? As I explained, we are gonna use the bootstrap algorithm. Basically, bootstrap is a very simple algorithm. It says that select randomly some samples from the original set to the newly created set. But you can select multiple times the same sample from the original set as long as the number will be equal to the original train set. So you see that B, D, D, C. Here we are missing A. We don't sample A in DS1, but we have double D here. Pay attention to the DS2. We have D, A, D, A. This time we are missing B and C, and we have double samples from D and A samples from the original. I think it is some simple idea. So in bootstrapping, our goal is to create as many as data sets where the trees exist in the random forest. And these data sets should be different from each other. And we let that the samples can replicate in that samples, in that train sets. I think it is clear. Any questions? Okay. Now we have the n number of trees, n number of data sets bootstrapped from the original train set. We can create these, or we can build these trees. However, the algorithm we described for the decision tree is slightly modified. Instead of looking for the best test for each node, in each node, the algorithm randomly selects a subset of the features. Here we mean that in the decision tree, remember that we built the tree such that the test questions can ask any questions from any feature in the train set. Here we are gonna limit from which features we can ask the questions. So in the data set we created by bootstrapping, we have the same number of features, but now we also limit the number of the features that can be used in training that specific decision tree in the forest. So we can use a subset of the features in the train for each decision tree. So the number of features that are selected is controlled by the number of attributes considered at each split parameter. Here you see that when you click this, you can put a number. So maybe in original data set, you have 15 features. Then you create by bootstrapping some data sets. In that data sets, still we have the same number of features. And you can limit for to 5, for example. It means that each decision tree randomly selects only 5 features out of 15 to build itself. So the question is why we do this thing. An answer? Any comment? Why we use a selection of subset of features randomly, not all of them? An idea?
Normalizing the outcome so we can avoid the overfitting.
Yeah, one result is like that, but there is much more important than this one.
Is it for the accuracy, teacher?
No, it can help, but it's not the main advantage. What is the main? So think about what is the whole concept about random forest. It's an ensemble method. It puts maybe hundreds of decision trees, right? If they are the same, do you think that is that any good to put them together to decide?
No.
Because they will vote in the end, right? Someone say this class is A, someone say B, someone says C, and you are gonna select, for example, majority of classes to decide the class of the test point, right? So in real life, do you want to create 100 voters and they are all the same? They decide all the same all the time. Do you want this?
No, because the problem may require otherwise.
So assume that you have 100 voters always like the cake, but never like the pasta. So do you think that they can give you a balanced vote for the tasting competition, for example?
No, no way.
No. They all be biased, right, against the pasta, but favor for the cake. So you don't like this, because if you collect 1 people or 100 people, doesn't make any change because they are all in similar minded people, right? So we try to create, as I explained, different trees, decision trees in the forest. Therefore, we try to build these trees differently by providing different data sets and different feature sets or subsets. Do you understand this?
Is it, teacher? Is it like we are creating a virtual? We are creating virtual people to
Train all,
doldurmak, yani
train
anketimizi
different,
doldurmak için virtual insanlar yaratıyormuşuz gibi mi davranıyor yani?
Yes, so we are creating decision trees. When we build these decision tree, we are giving different data sets and different features. We don't use the whole features. So let me go over here. Assume that that's our train set. In that train set, assume that we have 15 features. Okay. And in that train set, assume that we have samples A, B, C, D, E. And these features are begin from F0 and let's say F15. Okay. Now, we want to create a decision tree. Okay, one decision tree. But we provide this decision tree only a new data set. Okay. Again, it is 1, 2, 3, 4, 5 samples. 1, 2, 3, 4, 5 samples. But these samples are randomly selected from here. For example, it could be AA, B, B, B. So you see there is actually 2 samples actually. And if you set that as a parameter, my feature set will be only 3. Okay. Then you are gonna select only 3 samples from here. For example, F1, F5, and F6. So basically what you are gonna do, you are gonna use this data set to train that decision tree. Okay. And continue like that. Now you want to train the second decision tree. Okay. This time you are gonna select 5 samples again from here. 1, 2, 3, 4, 5. Assume that this time they are D, E, A, B, randomly select. And since the F is 3, selected the number of the decision, the number of the feature subset is 3. We randomly select the features, for example, F8, F10, F12. Now, what we are gonna do? We are gonna do this. We are gonna provide this train set to this decision tree. Do you think that these 2 decision trees could be similar to each other or could decide similar to each other? They cannot, because one of them you will use F1, F5, F6 to decide, and it's trained on AB samples only. But the second, the bottom decision tree only learns F8, F10, F12 features, only seeing the D, E, A, and B samples. So do you understand that? In the forest, assume that we train 100 decision trees with 100 different data sets and the features. So we are gonna combine, and at the end, after the training, we are gonna put all these into one ensemble network. Then we are gonna provide this data set or the train data set. Then we will run this. So algorithm will select these features from that questions for test this one. Then we are gonna select these features from that set to train, to test this one, and we are gonna combine the results of these decision trees as the decision of the random forest. Is that clear for everyone?
Yes. Also, sir, can I ask a question?
Yes.
Is there a number or percentage for choosing the F?
Yes.
Like we have 10 features. Three of them should be F or something.
For classification, we are gonna use the square root of the total features here. So if the total features is here and total features, we put here most probably for the classification square root. And for example, let's say that in the cancer data set we have 10 features. Okay, Wisconsin data set, everybody knows that 10 features. We are gonna put here 3, for example, as the selected F number. Okay.
Okay.
For the regression, I will give the formula right now. Okay. But do you understand the basic idea why it's called ensemble? Of course, think of that. There are hundreds of data sets created from here, the original data, and we have hundreds of decision trees trained with that data set. So we try to guarantee that each decision tree in the random forest are trained differently. Therefore, we build differently. And their decision depends on the, pay attention, For example, let's say that this is the decision tree 0. So decision tree 0 will be trained on A, B, B, on the A and B samples, and for F1, F5, F6. So actually, I can show like that. For example, it is seeing the partial of the data set. Am I right? It can overfit to the some part of the original data set. Am I right? Yes, no question.
Yes.
Yes.
Yes, only part of it, because it cannot see CD and D and the other features. So for the DT1, decision tree 1 in the random forest can only overfit some of these, right? For example, CD
Yes.
and the feature 5 or 6, 7, for example. So we ensure that none of the decision trees in the forest can overfit the whole part of the data set. So the total of the ensemble random forest cannot overfit at all. Do you understand?
Yes.
Yes, that's the idea. Any questions? Okay, and the same idea works here. Why we use the bootstrap sampling or bootstrapping? Everybody understands, I believe, huh?
That's clear.
Yes, now the data samples are different, right? So basically, we try to create new data sets for each decision trees in the random forest to train, to build up. Therefore, we are sure that each trees in the random forest are different. They can overfit, but overfit to only part of the data set samples and part of the subset of features, not all the features, not all the samples. So do you understand that by using random forest approach, ensemble approach, we can get rid of the overfitting problem in decision tree? Do you see this? Do you understand? Do you get it? So we can think, let's talk about more about the number of the attributes or the features. If I select the number of the features as 1, what happens?
There's only one tree, so it could overfit easily.
Only one? What?
Did
Only
I get
one?
wrong?
One feature.
I thought I heard a number of trees. Okay,
We are
there's
talking
only one feature. So we are basically deciding the outcome by only looking to individual features. So
what do you expect? Assume that we have hundreds of trees, okay, but we only use one feature in each decision tree, and assume that there are 15 features. Randomly select one of them each. So what happens? What could be the accuracy? What could be the overfitting? So do you think that the decision tree capacity is very limited, right? It tries to predict the result by using only one feature. Do you think that it is possible?
No, not only one
So
feature.
its capacity will be very, very low. But if I set these number of attributes as a number equal to the number of the features in the given, in the original data set, what happens? Assume that in the original data set we have 15. And in the, here we also have the 15. So what happens?
Nothing will change, I think.
But don't forget the bootstrap. So we have the 15, 15 means that Now you are giving all the features to all the decision trees. They can easily look like similar to each other, right?
Yes.
But don't forget, we have the bootstrap still. They are seeing different parts of the samples, but most likely the random forest can still have the problem of we don't have required randomness in the decision trees. Okay, so this number should be in between 1 and to the number of data sets in the feature in the data set. So you need to be careful and you need to play with it. If you go to the one scale up to the equal number in the data sets, then you will see that you will overfitting to the data. But if you go to the other side to 1, the number of the attributes, if you decrease it, then you will see that your random forest gets much more simpler. So it gets rid of the overfit. But after some point later, you will see that you will get underfit. Do you remember that underfit, overfit, and the sweet point? Remember? We have discussed. So here is that. The similar idea applies in linear models. Remember lasso and reach? We have the C, and the C number can be between, remember, -0 or to 1000, okay, for example. So when you begin with 1, if you go to increase this, you will see that you can get overfit. But if you decrease, at some point you get rid of the overfit, but after some point you get stuck to the underfit. That's the similar ideas. So pay attention to this. I will ask in your projects, why do you select this? And I will ask you in any exam. Okay. So if you set number of attributes to 1, that means that the splitters have no choice at all, because deciding only by using only one feature, and only search over different thresholds for the feature that was selected randomly. If we choose a high number of attributes, means that the trees in the random forest will be quite similar. And they will be able to fit the data easily using the most distinctive features, so they are similar. A low number of attributes means that the trees in the random forest will be quite different, and that each tree might need to be very deep in order to fit the data well, but each of them. So basically, we need to decide the number of these attributes and observing the train and test accuracies to decide the point between the underfit and overfit. Okay. How we do the prediction in that ensemble model, the random forest? To make a prediction using the random forest, the algorithm first makes a prediction for every tree in the forest. Assume that these are the waters each. So you provide the test point to each decision tree. They will take decisions and they will return you the decisions. For the regression, we get the answers from these decisions and you can get the average of the numbers because it's a regression problem. Then this number, the average one, is your regression result. In classification, we most of the time can use soft voting. So soft voting means that you don't say only the red class, but you say that as a one decision tree says that 0.85% is red point. Okay, that's soft voting. Hard voting, each decision tree only says red or black. Do you understand the difference between soft voting and hard voting? Or just voting? In soft voting, you provide your class prediction with a probability. Then we get these probabilities from each decision tree in the random forest and get average and then decide the class with some probability. Here you see the simple R synthetic data set, 2 moods data set. the trees that are built as part of the random forest are stored in the model. So in the random forest model, you will have, for example, if you have 10 or 100 forest decision trees, they will be in the model stored by their parameters. I mean the questions, right? The tests. You can visualize the decision boundaries learned by each tree, therefore, and together with their aggregate prediction as made by the forest. Now, pay attention there, please. This is decision tree 0. This is tree 1, tree 2, tree 3, and tree 4. So these are the trees in the forest. And pay attention that that's the random forest. Okay, so this is the collection of these trees results. The results. So you see the blue and red classes according to the feature, provide 2 features. And if you look at these, you can see that these randomly created trees, randomly means that bootstrapping in dataset and feature selection randomly. So if you notice that 5 trees, they have different decision boundaries. You see by your eyes, right? Decision boundaries. All right. Now look at the random forest. Now tell me that, do you think that which one has smoother boundaries? Smoother boundaries.
Tree number 2.
Smoother, not rigid. As you see that actually, all the decision trees have rigid, right? Look
Yes.
at all of them is line. You see that? All of the decision boundaries are line. Notice that? But look at the random forest. Do you think that these decisions are lines?
No, chains.
Yeah, it is smoother, right? Smooth. So it is somehow getting different from each of them, right?
Yes.
And it fits to the data better. You see that? It fits to the data better, but doesn't overfit. Interesting, right? So, for example, there is a blue. Here it does not go to get the blue to the blue side. Therefore, by your eyes, you can see that by creating different trees, random trees, okay, here 5 random trees, when you put the results, not the result, okay, the results together, you have a boundary here with a smooth. So it means that your model can fit to the data better than of each of them separately. But when you put together all of them, you have a better solution to the problem. So let's do the summary. So we have seen that each decision boundaries of each tree, 1, 2, 3, 4, 5, is totally different. You see that each of them has a different decision characteristics. And some of them make some mistakes. You see that, some mistakes. And you can notice that maybe these are all the test points, okay? Or I'm sorry, train points. And in some parts, they don't care about some train points because they don't have in their train set because of bootstrapping, right? So they have made some mistakes and they are not aware of that mistakes because they don't know these samples. We didn't provide these samples. And the random forest overfit less than any of the trees. If you look at these, they tend to overfit each of them. They are putting their decision boundaries such that maximize the accuracy, so they tend to overfit. But since each of them overfit to the separate subset of the data and subset of the features, when you put all together, you remove the magically you remove the overfit on the original data set. Okay. Now, how can we test in the orange tree? Actually, you know that on the model, I have already shared these models. You know that if you go to the Moodle models, you just click the OWL type files and you can just run it. You know that this is on the Moodle. So you can create the data sampler and test and score for train set and the test and score for test set, pay attention, and random forest. And you can add here the linear models to compare with it, the random forest. And there is the, here you can just visualize the resulting random forest. Okay. Let me go over step by step. And then I will go to the orange and share these details and see the result on the live example. Now pay attention that we have these parameters. So the number of trees is important, right? I will come to this, how to select. And number of attributes, replicable training. Okay, so you know that replicable training means that since we are creating random data sets for the trees, each time you are creating bootstrapping and selecting some features for each decision randomly. But each run, each test, it will be giving different results. In your projects, you need to select this replicable training by ticking it. Don't forget it. Otherwise, each run, you will have different results. When you are writing your project reports, and you know that you have the deliverables to me, these deliverables are your presentation, final report, and don't forget your orange model, OWL. Okay, so when you send me your OWL, if you didn't tick this replicable training, then the results that I am going to see in the orange and the result that you are reported in the report file will be different. Please click this replicable. Okay, don't forget this. Please, this replicable click. Okay, that's the one thing. I will come to the others, but for these ones, you might remember from last week, these are the control of pruning, right? Approaches for the decision trees. Remember last week. So limit the depth of the individual trees and do not split subsets smaller than this number of samples. So it means that we are gonna limit the depth of the tree by it means that we are trying to limit the prune the tree such that we try to get rid of the overfitting, correct, or too deep decision trees. Okay. What we see here that in the train we have the classification accuracy 100%, and in the test we have 95%. By in that example, in just that example, we use 100 decision trees in the forest, and for each training these trees, we use only 5 attributes out of 10 in the breast cancer dataset. I will provide the details, don't worry. Okay. In this example, if we add these SVM, logistic decision or tree algorithms, you can come up with different numbers each time. So it's a good idea to click this. Okay. And we have only 105 here, you see. And you can actually, at any time, you can come up with different numbers. I mean that your numbers could be different from my numbers because your computer random generation is different mine. And here, SVM is that point and the others results, you see that. And this is the classification for train. And this is the test. Okay. I will go over this here. Now we need to adjust the number of attributes, okay, and the pre-pruning rather than using these default values. Default values works well, but you need to still think about it. The strength of the random forest is that it is very widely used. As I said, that if you check the Kaggle competitions, still most of the people gets very competitive results with random forest and gradient boosted trees as well. And they don't have many parameters like in deep learning, they don't have. So it is very easy to decide about these parameters. And the best part of it that they don't require scaling. So remember that decision tree requires scaling? No, but linear algorithms require scaling of the features. And more essentially, random forests share all of the benefits of decision trees while making up some of their deficiencies. One reason to still use decision trees is if you need a compact representation of the decision-making process. It's basically impossible to interpret tens or hundreds of trees in detail, and trees in random forests tend to be deeper than decision trees because we are going to use the limited number of subsets, so it needs to use more rules to fit the data. If you need to summarize the prediction making in a visual way to non-experts, a single decision tree might be better choice. So you can begin to understand your data by using a single decision tree. Then understanding your data and working on the features, maybe. After you can switch to random forest to get a better prediction object regression. However, building random forest on large data sets might be somewhat time consuming. It is clear because we are creating hundreds of decision trees. However, you know that we are using multiple CPU cores and multiple hundreds or thousands of GPU cores. So today it's not a big deal. So you don't think about that's a big problem. So using parallel computation, it's a linear speeds up. It means that if you have 100, for example, GPU or CPU, then the training random forest will be 100 times faster. Okay, as I already explained, please keep in mind that the random forests by their nature are random because of bootstrapping and selecting the subset of features. And so selecting the different random states can drastically change the model that is built. So when I show you, now I'm going to show you some examples, you will see that the results of that examples will not always be as expected. You will see that this is not because I am mistaken, because it's initialized with a different random seed. So it's very subject to these random seed. Of course, the more trees in the forest, the more robust of the random forest. It means that to get a more powerful model, you need to increase the number of the trees, and you can limit the effect of the randomness. Starting the random generator with the seed can be avoided. Of course, as I explained, we always consider the reproducible results. So always click here, replicable training, don't forget. Okay, but random forest, as observed, don't tend to perform well on very high dimensional sparse data, such as text data. So high dimensional means that many number of features. Sparse data means that in the samples, most of the features have zero values or does not exist values. So it is not, the random forest cannot perform well. For this kind of data, as we know that linear models might be more appropriate. Random forests usually work well even on very large data sets. The number of the samples is high, and training can easily be parallelized over using many CPU and GPU cores. Random forests require more memory. Why? Because each decision tree is gonna be deep, and they will require more space. So training requires space in memory, not only speed, but space as well. Therefore, they are very slower to train compared to linear models, actually. And in the prediction time, you need to go over all of these trees until the decision. So it takes also much time compared to the linear models in prediction as well. Therefore, if the memory is a problem for you, it's a good idea to use linear models. For example, if you are creating a model to run on a smartphone, okay, so you don't want to use a random forest with 300 decision trees. Okay, there was a question about the number of attributes and the pre-pruning options. Okay, so we can go over and talk about these. Of course, the number of trees larger is always better as long as you have the memory, so your random forest can fit into your memory. Increase this number of trees. Okay, and we know that more trees will be actually more robust random forest and get rid of the overfitting. So reducing the overfitting is strange, because so far we learned that if we increase the capacity of a model, we learned that in the linear models, for example, we learned that the risk of overfitting is increasing as well. But here, it's not like that. So even you are increasing the number of the trees, you are reducing the overfitting. So it's good. However, always remember that it will take more time and more space. Here is the answer to the question, how can we decide the number of the subset of the features? So basically check for your original data set. If you have in the original data set add features, get the square root of this to decide the number of attributes in each decision tree in the random forest, if it is a classification. But if it's a regression, you can use log. Okay. Of course, as we know from decision trees, we need to use pruning techniques. In pre-pruning techniques, we can stop the building the tree when we face with some limitations. So we need to put the limitations to stop these trees getting deeper and deeper. Okay, so we have provided here in that orange tree tool the two things. The first one is, as you see here, growth control, so pre-pruning. The limit depth of the individual trees, you can put this, or do not split subsets smaller than this. So the number of the samples in the left node. Since we have discussed last week, I will not go over it. So in the next part, we are gonna go into deep about SVN. We have seen the linear SVN, but we are gonna see the kernel SVN in the next lecture. Do you have any questions?